Welcome to the Deep Dive, the show that cuts through the noise and gets you well informed on the most fascinating topics. And speaking of fascinating, just look up at the night sky tonight, or maybe even during the day if you know exactly where to look. After the sun and moon, there's one natural point of light that outshines everything else. That's our celestial neighbor, Venus. You've probably seen it as the morning star or evening star. Okay, let's unpack this. Today we're taking a deep dive into Venus Tenale. You know, the planet that's often called Earth's twin, but couldn't be more different in reality. We've gathered some really illuminating sources covering everything from its ancient mythological roots right up to the latest cutting-edge science and some pretty wild ideas for future human visits. Our mission is to figure out why this planet, seemingly so similar to ours, turned into such an extreme place.
Indeed, it's a planet of, well, profound contrasts, shrouded in thick clouds, hiding its secrets for so long. So our goal today is to sift through what we really know about Venus. How did it get its name? What are its incredibly hostile surface and atmosphere actually like? What about the amazing robotic missions that have braved that environment? And of course, the really big questions. Could life exist there? Maybe in the clouds? Could humans ever, call it home somehow?
Yeah, there are definitely some surprising facts that might make you rethink this veiled world. So let's dive right in with this whole Earth's twin idea. Why do we call it that? What are the basic physical similarities and where do they just completely break down?
That's the perfect place to start because it really gets at why Venus was initially so intriguing. Physically, Venus is remarkably similar to Earth in a few key ways. It's almost the same size. Its diameter is about 12,104 kilometers. Earth's is 12,742. Very close.
Okay, practically identical in size.
Exactly. And its mass is also very close to Earth's, which gives it a surface gravity of about 0.904 times Earth's gravity. Now, that might sound like a small detail, but it's actually really important when you think about future human space travel.
Right, because our bodies need gravity.
Precisely. It suggests the gravity would likely be enough to prevent the really severe bone loss and muscle weakening that astronauts face in microgravity over long periods. And if you look at how they formed, both planets came together from similar stuff in the early solar system nebula. This implies they probably started with similar geochemistry, and models even suggest both rocky planets initially had, well, a lot of water.
So if you just looked at the basic stat sheet, you'd think, wow, cosmic twins. But then you look closer, and the reality of Venus is just something else entirely. What are those stark, almost nightmarish differences that make it such a puzzle?
Yeah, the similarities, while interesting, they end pretty dramatically right there. Unlike Earth, Venus has absolutely no liquid water on its surface now. None. Its atmosphere is, well, monstrously thicker and denser than any other rocky planets in our solar system.
Much thicker than Earth's.
Oh, vastly thicker. It's mostly carbon dioxide, topped by this global layer of opaque sulfuric acid clouds that just completely hide the planet from view in visible light. And the conditions at the surface, they're truly infernal.
Infernal sounds about right. What are we talking, temperature-wise?
The average temperature is around 467 degrees Celsius. That's about 872 Fahrenheit. To put that in perspective, it's hot enough to melt lead, zinc, some rocks even.
Hotter than Mercury, even though it's further from the sun.
Exactly. And that's because of the atmosphere. The pressure is just as extreme, 93 bar. That's the equivalent pressure you'd feel if you were submerged about 900 meters, nearly 3,000 feet underwater here on Earth.
Wow. Imagine that pressure. Like a small car on every square inch.
That's a good way to think about it. It's crushing. So forget standing on the surface comfortably.
The atmosphere sounds like something truly alien. Can you paint a bit more of a picture? What's it actually made of, beyond just thick? What would it feel like down there, besides hot and crushing?
It's a truly bizarre environment. As I mentioned, it's overwhelmingly carbon dioxide, about 96.5%. Then there's about 3.5% nitrogen, and just trace amounts of other things like sulfur dioxide, argon. But because of that intense temperature and pressure right down at the surface, the carbon dioxide and nitrogen exist as what we call supercritical fluids.
Supercritical, what does that mean?
It means they're in this weird state where they're not quite liquid, not quite gas. They sort of behave like both at the same time. Think of it like a thick, incredibly dense, soupy fog, but with a density around 65 kilograms per cubic meter. That's about 6.5% the density of water, but still 50 times denser than Earth's air at sea level.
50 times denser.
Yeah. And this hyperdense CO2 atmosphere is exactly why Venus has the strongest greenhouse effect in the whole solar system. It just traps an enormous amount of heat. That's why it's hotter than Mercury. Carl Sagan famously pointed to Venus as this Stark warning about climate change on Earth. He called it a greenhouse inferno.
A greenhouse inferno. It's a sobering thought, isn't it? A potential future if things go really wrong.
It absolutely is. It shows what can happen when a planet's atmosphere tips into a runaway state. The positive feedback loops, more heat leads to more greenhouse gases, which leads to more heat, can potentially irreversibly transform a world.
So is that fate inevitable for planets like Earth, or did Venus just lack something crucial?
That's the critical question Venus forces us to ask. Its runaway effect suggests there is a tipping point. On Earth, we have active plate tectonics and large oceans that act sort of like a thermostat, a carbon pump, pulling CO2 out of the atmosphere and locking it into rocks over geological time. Venus seems to lack this planet-wide process now, so the CO2 just built up.
So plate tectonics might be key to long-term habitability.
It seems very likely, yes. Venus shows us how critical that balance of greenhouse gases and geological activity really is. It's not necessarily inevitable for all Earth-like planets, but Venus is our cautionary tale right next door.
And those clouds, sulfuric acid, that just adds another layer of nope
Yeah,
to the whole environment.
it really does. These thick, opaque clouds of sulfuric acid droplets blanket the entire planet, stretching from about 45 up to 70 kilometers in altitude. They're why we couldn't see the surface optically for so long, why we needed radar.
How does sulfuric acid even form up there?
It's a photochemical process happening high up. Ultraviolet light from the sun breaks down CO2, sulfur dioxide, and water vapor. The bits recombine to form sulfur trioxide, which then reacts with the tiny bit of water vapor available to make sulfuric acid, H2SO4.
So it literally rains acid.
Well, yes and no. Sulfuric acid rain does form in the clouds, and they are incredibly acidic, think battery acid, maybe pH 1.0 or so. But here's the bizarre thing. The rain never actually reaches the ground.
It evaporates before it gets there.
Exactly. Because the temperature and pressure increase so dramatically as you go down, the acid droplets evaporate long before they hit the surface. It's a phenomenon called virga. You see streaks of precipitation that just vanish midair. Surface humidity is incredibly low, less than 0.1%.
Virga. Acid rain that doesn't rain. Venus just keeps getting weirder. Can we see different layers in these clouds? And what about the super rotation I've heard about?
Yes, we can see layers, especially using infrared imaging. Different altitudes have different cloud densities and maybe compositions. You see hazes stretching even higher, up to 90 kilometers. Reddish clouds tend to be the highest, green and blue lower down. But the super rotation, that's one of Venus's biggest mysteries. The solid planet itself turns incredibly slowly. One rotation takes 243 Earth days.
Yeah.
A Venusian day is actually longer than its year.
Longer than its year? How does that even work?
It's bizarre, isn't it? It orbits the sun in about 225 Earth days. But while the planet creeps along, the entire atmosphere whips around it much, much faster. At the cloud tops, winds can reach speeds of 360 kilometers per hour. That's 220 miles per hour. Whoa.
Yeah, they circle the entire planet in just 4 Earth days. So the atmosphere is racing around almost 60 times faster than the ground below it.
What drives that? How can the air move so much faster than the planet?
That's the puzzle. The leading theory involves thermal tides, atmospheric waves, caused by the sun heating the day side intensely. This somehow transfers angular momentum, like a giant atmospheric engine, pushing the atmosphere around from day to night, creating this incredibly fast global flow. But the exact mechanics are still being debated and modeled.
Okay, so we have this crushing, sizzling, acidic, super rotating atmosphere hiding the surface. What about the ground itself? What does it look like under those clouds? Getting any information must have been incredibly tough.
Monumentally tough. It took radar mapping, mainly from the Magellan mission, to really peel back the veil. What we found is that about 75% of the surface is bare rock, mostly volcanic bedrock. There are only thin, patchy layers of regolith loose rock and dust.
Not like the moon or Mars with thick, dusty layers. Exactly, much less broken up material. What's also really striking is how few impact craters there are, especially small ones. You won't find any crater smaller than about 3 kilometers across.
Why is that?
Because that incredibly dense atmosphere acts like a shield. Smaller incoming asteroids or comets just burn up or break apart completely before they can hit the ground. Anything less than maybe 50 meters wide probably won't make it.
So the atmosphere protects the surface from small impacts.
Yes, but the overall lack of large craters is also significant. It suggests the surface is relatively young, geologically speaking, maybe only 300 to 600 million years old on average.
Young compared to...
Compared to the Moon or Mars, whose surfaces have craters dating back billions of years. It strongly suggests that Venus underwent some kind of catastrophic planet-wide volcanic resurfacing event, or maybe several, that basically paved over its older history. It's a completely different geological story than Earth's slow, steady plate tectonics.
Wow, paved over by lava. Does that mean Venus is still volcanically active today, or did this all happen hundreds of millions of years ago?
That's a question where the science has done a complete 180 in the last decade or so. For a long time, the thinking was, yeah, Venus had this massive resurfacing event, but it's pretty quiet now. But in the last 15 years, that view's been completely overturned. Volcanism seems to be the dominant geological force, and yes, it appears to be ongoing.
Ongoing, like right now.
Very likely, yes. There's mounting evidence. Recent analysis from 2024 pointed to potential new lava flows on Sif Mons and Niobe Planitia. Back in 2006-2014, the European Venus Express orbiter detected hotspots areas much hotter than their surroundings on a volcano called Aydin Mons. These suggested lava flows that could be incredibly young, maybe only a few hundred to a few thousand years old.
Geologically speaking, that's basically yesterday. How can they tell the age so precisely?
It's really clever lab work, actually. Scientists simulate the Venusian atmosphere and see how quickly common volcanic minerals, like olivine found in basalt, change or weather in that environment. They react really fast, weeks to months. So, if a spacecraft sees the infrared signature of fresh, unweathered lava minerals on the surface, that lava can't be very old at all, maybe only a few years old because it would have chemically changed otherwise. It's strong evidence for very recent, possibly current eruptions.
That's amazing detective work. Are there other signs of this activity? What kind of weird volcanic features does Venus have?
Oh, yes. A big study in 2020 identified 37 corona, these huge circular fracture patterns linked to mantle upwelling that appear to be currently active. And even more compelling, research in 2023, reanalyzing old radar data from the Magellan mission in the 90s, found a volcanic vent that visibly changed shape over just 8 months. It expanded by almost 2 square kilometers.
Wow, actual change captured between images.
Exactly, direct evidence of structural change. So, Venus is definitely not geologically dead. And beyond active spots, it has unique landforms. You get shield volcanoes, like on Earth, but also these things called pharra. They look like giant flat pancakes, maybe 20, 50 kilometers across, formed by thick, gooey lava. Then there are arachnoids, which look like spider webs of fractures, and those corona we mentioned, all volcanic.
Pancake domes and arachnoids. Sounds otherworldly.
It is. And the lava flows themselves can be enormous, hundreds of kilometers long, much bigger than on Earth, probably due to very fluid lava and the high surface temperature keeping it molten longer. They carve these vast channels called canali. The longest one, Baltusvelis, is over 6,800 kilometers long. That's like 1/6 of the way around the planet.
Incredible scale. Okay, so it's volcanically active, maybe very recently. What about deep inside? Is the internal structure like Earth's under all that rock? And what about a magnetic field?
The current thinking is, yes, the basic internal structure is probably quite similar to Earth's. A metallic core, likely iron and nickel, surrounded by a silicate mantle and then a crust. The crust is estimated to be maybe 20, 25 kilometers thick, similar to Earth's continents. The mantle is probably about 2,840 kilometers thick, and the core radius is thought to be around 3,000 to 3,500 kilometers.
So core, mantle, crust, just like home.
Pretty much. The similar size and density suggest they've probably cooled at roughly similar rates, implying the core might still be partially liquid, like Earth's.
But does it have a magnetic field like Earth's? That seems pretty important.
Ah, and here's another major difference. Venus has a very, very weak magnetic field. And critically, it's not an intrinsic field generated by a dynamo in the core, like Earth's.
No dynamo. Why not? If it's Earth-sized and might have a liquid core.
That's the surprise. A dynamo needs 3 things: a conducting liquid core, convection, churning motion within that core, and reasonably fast rotation. Venus probably has the liquid core part, but it rotates incredibly slowly, and crucially, it seems to lack significant convection in its core.
I know convection.
One leading theory connects it back to that potential global resurfacing event. If Venus lost its plate tectonics and developed a thick, stagnant lid crust, it might have trapped heat in the mantle. This would insulate the core, reducing the heat flow out of the core. Without enough heat escaping, the core wouldn't churn, the dynamo wouldn't start, or it would shut down.
Okay, so no internal dynamo. What kind of magnetic field does it have then?
It has what's called an induced magnetic field. This is created by the interaction between the solar wind, that stream of charged particles from the sun, and Venus's upper atmosphere, its ionosphere. It's much weaker and doesn't provide the same kind of protection as Earth's global field.
What does that lack of protection mean for Venus?
It's profound. The solar wind slams directly into Venus's upper atmosphere. It can strip away atmospheric gases, especially lighter ones. Ultraviolet light from the sun splits water molecules into hydrogen and oxygen. The solar wind then energizes these ions, especially the light hydrogen, giving them enough speed to escape Venus's gravity forever.
So that's where all the water went, stripped away by the sun.
That's the dominant theory, yes. This atmospheric erosion, happening over billions of years because there's no magnetic shield, likely removed most of Venus's initial water, leading to the incredibly dry planet we see today. We can see evidence of this ongoing loss in the atmosphere's deuterium to hydrogen ratio. Deuterium is heavy hydrogen. Because the lighter hydrogen escapes more easily, the remaining atmosphere is enriched in deuterium, about 100 times more than elsewhere in the solar system. It's like a fingerprint of planetary dehydration.
It really makes you appreciate Earth's magnetic field. Okay, let's rewind the clock. Before we sent probes, before radar mapping, how did people see Venus, this super bright object in the sky? What did ancient cultures make of it?
Oh, it's got a fascinating history woven into human culture. Being the third brightest thing in the sky after the sun and moon, it's been known since prehistory. Its brilliance made it stand out, an object of wonder, worship, and careful observation across countless ancient societies.
I can imagine. And it does that thing where it appears sometimes in the morning, sometimes evening. Do they always realize it was the same thing?
Not always, no. Because it seems to disappear near the sun for a while, then pop up on the other side of the sky, many ancient cultures thought it was two different stars, a morning star and an evening star. The ancient Greeks, for example, called the morning star Phosphorus and the evening star Hesperus.
Two separate entities.
Initially, yes. But some cultures figured it out quite early. The ancient Sumerians, for instance, we have records like a cylinder seal from maybe 3000 BC, and later Babylonian tablets like the Venus tablet of Ammisaduqa from around the 17th century BC that show they knew it was a single object and tracked its movements very accurately. The Maya civilization in Mesoamerica were also incredible Venus observers. Their calendars and even warfare strategies were sometimes linked to Venus's cycles. They tracked it meticulously.
That's amazing precision for ancient times. How did they connect it to their gods and goddesses?
It was often linked to powerful, sometimes dualistic deities. The Sumerians associated it with their most important goddess, Inanna. She was complex, a goddess of love, fertility, beauty, but also of war and destruction.
Love and war. That's quite a combination.
It is, and that duality carried over. Later, Akkadians and Babylonians knew her as Ishtar, who had very similar roles presiding over both birth and death, passion and conflict. It reflected the planet's own changing appearance, perhaps. The name we use, Venus, comes directly from the Romans. They named it after their goddess of love, Venus.
The Roman Venus. Tell us a bit more about her role. Was she just about love?
She was much more than just love, though that was central. Venus encompassed beauty, desire, sex, fertility, prosperity, and even victory. Mythologically, she was considered the ancestor of the Roman people through her son Aeneas, the Trojan hero who founded the lineage leading to Rome.
So a foundational figure for Rome itself.
Absolutely, and figures like Julius Caesar actively claimed descent from her to boost their prestige and authority. She had many different cult titles reflecting her aspects. Venus Urania was Heavenly Venus, representing pure love. Venus Verticordia was the changer of hearts, guiding desire towards marriage. And Venus Victrix was Venus the Victorious, a more warlike aspect invoked for military success by generals like Sulla and Caesar. It's also interesting that our weekday Friday comes from the Germanic goddess Frigg, who is often equated with the Roman Venus.
Wow, such a rich history. Okay, so from goddess to, well, planet. When did the shift happen? When did we start seeing Venus through a scientific lens?
That really kicked off with the invention of the telescope in the early 17th century. Galileo made a pivotal observation. He looked at Venus through his telescope and saw that it showed phases, just like our moon full gibbous crescent.
Phases. Why was that so important?
Because the only way Venus could show a full range of phases, from crescent to full, was if it orbited the sun, not the Earth. The old geocentric model where everything circled Earth couldn't explain a full Venus. Seeing those phases was direct, visual proof supporting Copernicus's heliocentric model. It fundamentally changed our understanding of the solar system and our place in it.
A universe-shattering observation, literally. What about figuring out it had that thick atmosphere? When did that discovery happen?
That came later, in 1761, during a rare event called a transit of Venus, when the planet passes directly in front of the sun. A brilliant Russian scientist, Miguel Lomonosov, was observing it carefully. As Venus began to move off the sun's disk, he noticed a faint arc of light, like a little halo, around the edge of the planet. Yes. He correctly deduced this was sunlight bending or refracting through an atmosphere surrounding Venus. That atmosphere was scattering the light, creating the visible arc. It was the first real evidence. This was confirmed later by astronomers like Johann Schroeder in 1790, who saw the horns of a crescent Venus extending further than they should geometrically, again due to atmospheric light scattering. And Chester Smith Lyman later saw a complete ring of light around the dark side near conjunction more strong proof.
And those transits, besides revealing the atmosphere, they were used for something else really important in astronomy, weren't they?
They were hugely important historically. For centuries, observing transits of Venus from different locations on Earth simultaneously was the best way astronomers had to measure the astronomical unit, the fundamental distance between the Earth and the Sun.
How did that work?
By carefully timing when Venus entered and exited the sun's disk from widely separated locations, you could use parallax, the apparent shift in position in trigonometry, to calculate the Earth-Sun distance with unprecedented accuracy for the time. Knowing that distance allowed scientists to calculate the size of the entire solar system. Jeremiah Horrocks made the first known scientific observation of a transit way back in 1639, and famous expeditions like Captain Cook's voyage to Tahiti in 1768 were specifically funded to observe these transits for this purpose.
A global scientific effort hinging on these rare events. When was the last one?
The last pair happened relatively recently, in 2004 and 2012, but they occur in pairs separated by over a century, so the next pair won't be until December 2117 and 2125, so none of us here will likely see the next one.
Definitely puts astronomical time in perspective. What about the ashen light? Is that another one of these long-standing Venus mysteries?
Yes, the ashen light is a classic one. It's this faint, mysterious glow, sometimes reported on the dark night side of Venus when the planet is visible as a thin crescent. The first claims go back to the 1640s, but it's always been elusive. Some skilled observers see it, others don't.
What could be causing it? Lightning?
That was one popular theory for a long time, maybe massive, continuous lightning storms illuminating the clouds from below. Another possibility is it's just an optical illusion, a contrast effect in the observer's eye. But recently, data from NASA's Parker Solar Probe, which flew by Venus, points towards night glow as the most likely culprit.
Night glow, like on Earth.
Similar idea. Atoms and molecules in the upper atmosphere get excited by sunlight on the day side, and then they release that energy as faint light when they rotate onto the night side. Parker saw this glow, and it seems a better fit than widespread lightning, though lightning on Venus isn't completely ruled out.
Okay, so from naked eye observations and early telescopes, we move into the space age. Venus must have been a huge target, especially with the Cold War rivalry. What were those first daring missions like? What did they find, and what challenges did they hit?
Oh, absolutely. The space age turned Venus into a major focus, especially for the Soviet Union. They really poured resources into their Venera program. Before that, the U.S. Mariner 2 was the first successful planetary flyby in 1962. It confirmed the incredibly high temperatures, the high pressure, the thick clouds, basically confirming it was not a tropical paradise as some had hoped.
Yeah, the Soviets really went all in on Venus, didn't they? Despite a lot of early failures.
They were incredibly persistent. It was a real national priority. Their early Venera probes often failed en route or during entry. Venera 4 in 1967 was a partial success. It entered the atmosphere and sent back data, teaching us about the composition, but it also taught a harsh lesson. It got crushed by the immense pressure about 25 kilometers up, way before reaching the surface.
Crushed. So they drastically underestimated the pressure.
Dramatically underestimated it. It forced a total redesign. They had to build landers like tanks, basically. Venera 7 in 1970 became the very first spacecraft to successfully land on another planet and transmit data from the surface. It only lasted 23 minutes before succumbing to the heat and pressure, but it was a monumental first.
23 minutes on that surface.
Yeah.
An amazing achievement.
Truly groundbreaking. Later Venera missions got even better. Venera 9 and 10 in 1975 had both orbiters and landers. The landers survived longer, and Venera 9 sent back the first images from the surface, grainy, black and white pictures of a rocky, desolate landscape. Venera 13 and 14 in 1982 sent back the first color images, showing brownish-orange rocks under that thick, orange-tinted sky. They also carried instruments that drilled into the rock and analyzed samples. These missions were incredibly bold and gave us our first ground truth.
Actual pictures from hell.
Mhm.
So while the Soviets focused on landing, what was NASA doing? How did later missions build on this?
NASA took a slightly different tack initially. Their Pioneer Venus mission in 1978 consisted of an orbiter and a multiprobe. The multiprobe released 4 smaller probes that plunged into different parts of the atmosphere simultaneously, measuring conditions at various altitudes. That gave us a great profile of the atmosphere's structure.
4 probes at once.
Yeah, a very clever way to get widespread data. Then there was the joint Soviet-French Vega program in 1985. As their spacecraft flew past Venus on their way to Halley's Comet, they dropped 2 instrumented balloons into the atmosphere. These floated at around 54 kilometers altitude in that more temperate zone for about 2 days, measuring winds and conditions.
Balloons on Venus, that's wild.
Isn't it? Then, NASA's Galileo probe flew past Venus in 1990 on its way to Jupiter. It used infrared cameras to peer through the clouds somewhat, revealing smaller cloud structures and hints of surface features based on heat variations. But the real revelation in understanding the surface came with NASA's Magellan mission from 1990 to 1994. Since visible light can't get through the clouds, Magellan used powerful radar.
Bouncing radio waves off the surface.
Exactly. By sending radar pulses down and timing the echoes, it built up incredibly detailed topographic maps of over 98% of the planet. Magellan revealed all those amazing volcanic features we talked about. The pancake domes, the arachnoids, the vast lava plains, the canali, the coronae. It showed us what Venus really looked like beneath the clouds.
What else did Magellan find? Did it see the Venus snow?
It did. It imaged highly reflective areas on the tops of the highest mountains. It's not water snow, obviously. It's far too hot. It's thought to be some kind of metallic frost, maybe lead sulfide or even elemental tellurium that condenses out of the atmosphere only at those higher, slightly cooler altitudes. Magellan also gave us super precise measurements of Venus's slow rotation and even detected slight variations in the rotation rate, which hints at interactions between the solid planet and its thick atmosphere, or maybe processes within the interior.
Metallic snow.
Mm-mm.
Venus never fails to surprise. What about more recent missions from Europe or Japan?
Yes, after Magellan, the European Space Agency's Venus Express orbiter operated from 2006 to 2014. It made significant discoveries. It confirmed lightning signatures, Whistler waves, suggesting lightning might be fairly common, though the rate is still debated. It discovered a huge, swirling double vortex at the South Pole in the atmosphere, and, importantly, it found an ozone layer high up, similar to Earth's.
Ozone on Venus.
Yes, formed by sunlight acting on CO2. Venus Express also provided that key early evidence for recent volcanism with those infrared hotspots on Idun Mons. Then there's Japan's Akatsuki orbiter, which arrived in 2015 after a tricky orbital insertion. It's still operating and focuses purely on the atmosphere. It observed gigantic atmospheric waves, stationary bow waves stretching thousands of kilometers, likely caused by wind flowing over mountains far below. Interestingly, Akatsuki's data suggests a very low lightning rate, adding to the ongoing debate.
So the lightning question is still up in the air, so to speak.
Pretty much. And most recently, NASA's Parker Solar Probe, though designed to study the sun, has made several Venus flybys for gravity assists. It managed to capture surprising images of the nightside surface in visible and near-infrared light, wavelengths that can just peek through the clouds under certain conditions, confirming the topography seen by Magellan's radar.
It really feels like after a bit of a lull, maybe focusing on Mars, Venus is back in the spotlight. Is that fair to say? What's coming up next?
That's absolutely fair. For a while, the extreme surface conditions made Venus seem less tractable than Mars. But the atmospheric mysteries, the evidence for recent volcanism, and the questions about past habitability have definitely spurred a resurgence. NASA has 2 major missions planned reflecting this. First up is DAVINCI.
DAVINCI. What's the goal there? Deep atmosphere investigation, it sounds like.
Exactly. DAVINCI stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging. It's ambitious. It has an orbiter for remote sensing, but the main event is a descent probe. This probe will plunge through the atmosphere, taking measurements all the way down.
Like the old Venera probes, but with modern tech.
Precisely. It'll be the first probe to enter Venus's atmosphere since the Soviet Vega balloons in '85 and the first NASA atmospheric probe since Pioneer Venus in '78. Its main job is to measure the detailed chemical composition, especially noble gases and trace gases, in the lower atmosphere. This is crucial for figuring out Venus's water history. Did it have oceans? And understanding volcanic outgassing, and ultimately why it diverged so dramatically from Earth.
We'll take pictures on the way down?
Yes, it aims to capture high-resolution images of those mysterious tesserae terranes, ancient, complex, fractured highlands. These would be the first descent images since Venera 14 back in 1982. It's carrying sophisticated spectrometers and sensors to sniff out the atmospheric composition and structure.
Sounds fantastic. And the other NASA mission?
That's VERITAS, Venus emissivity, radioscience, INSAR, topography, and spectroscopy. Its launch is currently slated for maybe 2030 or later, but its goal is to map the surface geology in even greater detail than Magellan, using advanced radar. It will look for active volcanic flows, study rock composition using emissivity, how surfaces radiate heat, and create global topographic maps. If it overlaps with other missions, we could track surface changes over time. ESA, the European Space Agency, also has a big Venus orbiter planned called EnVision, with similar goals of studying geology and atmosphere interaction.
And isn't there a private mission, too, focused on life?
Yes, that's the Venus Life Finder mission being developed by MIT researchers, with Rocket Lab providing the launch and spacecraft. It's a smaller, targeted mission specifically designed to dip into the clouds and look for complex organic molecules or other potential biosignatures. It really speaks to the renewed excitement about that very possibility.
Right. Which brings us to the big one, life. With Venus being such a, hellscape now, it seems impossible. But was it always like this? Could it have been habitable way back when?
That's probably one of the hottest topics in Venus science right now. Was Venus ever habitable? Could it have had oceans? Climate models, particularly from NASA's Goddard Institute for Space Studies, suggest maybe. Their simulations indicate Venus could have had a shallow liquid water ocean for potentially up to 2 billion years early in its history.
2 billion years with water. That's a long time.
A very long time. Enough time, potentially, for life to arise if the conditions were right. These models suggest the final water might not have evaporated until maybe 715 million years ago. And adding to that, some recent studies analyzing radar data suggest Venus might have even had Earth-style plate tectonics billions of years ago.
Plate tectonics, too. Like a true twin back then.
It's a tantalizing possibility. Plate tectonics could have helped regulate the climate, maybe keeping it stable for longer. But something clearly went wrong.
What happened to the water then? If it had oceans, where did it all go? We know it's bone dry now.
It comes back to that runaway greenhouse effect and the lack of a magnetic field. As the sun got slightly brighter over billions of years, Venus heated up. More water evaporated, acting as a greenhouse gas itself, trapping more heat, causing more evaporation. A vicious cycle.
Runaway feedback loop.
Exactly. Once it got hot enough, and without a magnetic field to protect the upper atmosphere, solar UV radiation split the water vapor into hydrogen and oxygen. The light hydrogen escaped into space, stripped away by the solar wind over eons. The oxygen likely reacted with surface rocks or also escaped. We see the leftover signature today in that high deuterium to hydrogen ratio.
So the water was essentially cooked off and blown away.
That's the leading scenario. However, it's fair to say there is a competing hypothesis. Some scientists argue, based on atmospheric chemistry and perhaps the composition of volcanic gases, that Venus might have formed relatively dry and never had significant oceans to begin with. Settling this wet Venus versus dry Venus debate is a huge goal for missions like DAVINCI. Knowing how much water Venus started with is key to understanding its whole evolution.
A fundamental question. Okay, so maybe habitable in the past, but what about now? If the surface is completely out, is there anywhere else life might cling on?
Well, if you're looking for life on Venus today, you have to look up, way up into the clouds. The surface is just too hostile for life as we know it. But the idea of life in the clouds actually goes back decades to Carl Sagan and Harold Morowitz in 1967.
Sagan again. What was his idea?
They speculated that maybe microorganisms, extremophiles, could exist floating in the upper atmosphere, specifically in a layer roughly 50 kilometers or 30 miles up.
Why that altitude?
Because remarkably, at that height, the temperature and pressure are surprisingly Earth-like. Temperatures range from maybe 30 to 80 degrees Celsius warm, but potentially tolerable for some microbes, and the atmospheric pressure is about the same as Earth's surface.
Earth-like conditions.
Yeah.
Floating in the Venusian sky.
In terms of temperature and pressure, yes. It's sometimes called the habitable zone of the Venusian atmosphere.
Hmm.
Below that layer, it gets too hot. Above it, the solar UV radiation gets too intense. But there's a catch, a big one.
The sulfuric acid crack.
Exactly. That potentially habitable layer is right smack in the middle of those incredibly acidic sulfuric acid clouds. Any life there would have to be thermoacidophilic heat and acid-loving and have some serious protection against being dissolved, maybe protective shells or unique biochemistry.
Okay, so a very specific niche. If it exists, this must be where the phosphine story comes in. That caused a huge stir in 2020.
It absolutely did. A team led by Jane Greaves at Cardiff University announced they had detected phosphine gas, pH3, in that specific cloud layer, around 50 kilometers up. Now, phosphine is interesting because, on Earth, it's strongly associated with life produced by anaerobic microbes in places like swamps or animal guts. Industrial processes also make it, but finding it naturally usually points to biology.
And they couldn't explain it non-biologically on Venus.
That was the claim. The team looked at all known non-biological ways phosphine could be made under Venusian conditions. Volcanism, lightning, meteor impacts, weird atmospheric chemistry, and concluded none of them could produce the amount they thought they detected. Plus, phosphine should be destroyed relatively quickly by the chemistry in Venus's clouds, so finding it implies something is actively making it right now.
So life became the least unlikely explanation.
That was the provocative suggestion. Yes, it didn't prove life, but it put it seriously on the table as a possibility that needed investigation. Of course, it immediately sparked huge debate and controversy in the scientific community.
I remember the headlines. And something about penguins.
Ah, yes, the penguins. That was a funny side note. In explaining that phosphine is a biosignature on Earth, the scientists mentioned, correctly, that it's produced by penguins in their guano via microbes. The media sort of ran with it, leading to jokes about penguins in Venus's clouds. The point was simply that biology makes phosphine here, not that penguins are on Venus.
All right, good clarification. So where did the science land on phosphine? Was the detection confirmed?
It's still debated, honestly. Some follow-up studies, reanalyzing the data or using different telescopes, failed to confirm the detection or suggested the signal might be contamination from sulfur dioxide, which absorbs at similar wavelength. However, the original team and some independent groups reanalyzed the data and maintain they still see a phosphine signal, perhaps at lower levels than initially thought.
So the jury's still out, but it definitely spurred interest.
Massively. Regardless of the final confirmation level, the phosphine debate absolutely revitalized interest in Venus astrobiology. It highlighted how little we know about Venus's atmospheric chemistry and directly motivated missions like the Venus Life Finder to go and actually look for organic molecules in the clouds. NASA's administrator even called it the most significant development yet in the search for extraterrestrial life at the time.
If we are sending probes to look for life, or even thinking about future human missions, what about planetary protection? We don't want to contaminate Venus with Earth microbes.
Right. That's a huge ethical and scientific concern. Venus is currently classified under planetary protection category 2. That means there's considered only a remote chance that Earth microbes on a spacecraft could survive and reproduce on the surface because it's so harsh, but the atmosphere is different.
Because the clouds are more habitable?
Potentially, yes. If there is a niche for life in those clouds, we absolutely don't want to contaminate it with Earth life before we've had a chance to find out if anything native is there. It would confuse the search immensely. So any probes specifically targeting the potentially habitable atmospheric layers, especially those looking for life signs, need very stringent sterilization protocols. Uncrewed probes are definitely the way to go for now.
Okay, so looking for microbes in the clouds is one thing. What about humans? Could we ever actually stand on Venus? Plant a flag?
Standing on the surface. Realistically, probably never for any significant length of time. The conditions are just too extreme. 467 Celsius temperatures would melt standard electronics, solder, almost instantly. Even hardened electronics would struggle long term. The crushing 93 bar pressure, the corrosive atmosphere, it's beyond current technology for human suits or habitats on the ground.
Even robots struggle, right?
Absolutely. Even robotic exploration is incredibly difficult. Landers have only survived for a couple of hours at most. There's research into high-temperature electronics using materials like silicon carbide that might eventually allow for longer-lived surface missions, but building complex systems that can endure those conditions for days or weeks. That's still a huge engineering hurdle, likely decades away. Some concepts even involve dumb rovers on the surface being controlled by flyers overhead to keep the sensitive electronics out of the heat.
Okay, so surface is out. But you mentioned living in Venus, these cloud cities. That sounds like pure science fiction, But is it actually feasible?
It sounds like sci-fi, but it's surprisingly plausible from an engineering standpoint, much more so than surface colonies. The idea, explored seriously by engineers like Jeffrey Landis and even NASA concepts like KVOC, is to build habitats that float in the atmosphere, like giant airships or balloons.
Floating cities, where would they float?
In that sweet spot we talked about, around 50 kilometers altitude, up there, the temperature is a comfortable 0 to 50 Celsius, and the atmospheric pressure is about 1 Earth atmosphere.
1 atmosphere. So you wouldn't need a pressurized habitat.
Exactly. That's the killer app for Venus cloud cities. The pressure inside the habitat could be the same as outside. If you got a leak, it wouldn't be an explosive decompression like in space or on Mars. Air would just slowly mix, giving you plenty of time for repairs.
And stepping outside.
You wouldn't need a bulky pressure suit. Just breathing air and oxygen supply and protection from the acidic haze, maybe thermal protection depending on the exact altitude. Plus, the thick atmosphere above provides excellent radiation shielding, comparable to Earth.
How would these habitats float? Helium.
You wouldn't even necessarily need helium. Because Venus's atmosphere is mostly dense carbon dioxide, regular breathable air, our mix of nitrogen and oxygen is actually lighter than the surrounding Venusian air. So you could literally fill your habitat with breathable air and it would float like a balloon. It provides about 60% of the lifting power helium would give you here on Earth.
Fill it with air and it floats.
That's
amazing. What are the big challenges then? It sounds almost too good to be true.
Oh, there are still huge challenges. Getting the building materials there would be incredibly expensive. Whether launched from Earth or maybe sourced from asteroids, you'd need materials highly resistant to sulfuric acid corrosion, things like Teflon, PTFE, or advanced ceramics. Life support would need to be fully closed loop. Growing food would be essential. Power could come from solar panels, as you're above most of the clouds. NASA's AVOC concept, high-altitude Venus operational concept, actually sketched out designs for inflatable airships and habitats for month-long crewed missions in the clouds.
So people have seriously thought about the engineering. What about long-term exploration there? Could robots stay up indefinitely?
Landis proposed concepts for solar-powered airplanes or flyers that could operate perpetually in that 45-60-kilometer altitude range. Venus is cloudy, but it's closer to the sun, and sunlight reflects off the cloud tops too. So solar panels on both sides of the wings could generate continuous power as the flyer slowly circles the planet, staying in sunlight. These could monitor the atmosphere indefinitely, or, as mentioned, maybe control simple rovers on the surface below via radio link.
Okay, cloud cities and perpetual flyers. Fascinating ideas. Beyond just living at Venus, could it play a role in exploring further out, maybe as a stepping stone to Mars?
That's another really interesting angle being considered. A long-duration human mission to Venus orbit, or even a flyby, could be a valuable intermediate step between moon missions, weeks, months, and Mars missions, potentially 3 years round trip.
How would that help with Mars?
A mission lasting maybe 1-2 years in the Venus system would allow us to test and validate critical deep space technologies. Long-duration life support, radiation shielding, psychological countermeasures for isolation, deep space navigation, and operations. Basically, a shakedown cruise before committing to the much longer Mars journey. Astronauts near Venus could also teleoperate robots on the surface or in the atmosphere in near real time without the long communication delays you get between Earth and Mars. That would allow for much more efficient robotic exploration.
Practicing for Mars, closer to home, relatively speaking.
Exactly. And here's a quirky fact. In terms of travel time and trajectory opportunities using minimum energy, Venus is actually better positioned as a waypoint to the asteroid belt than Earth or Mars are. Its higher orbital speed gives you a boost. So maybe future asteroid mining operations could stage out of Venus orbit. It's a possibility.
Venus is a gateway to the asteroids. Never thought of that.
Yeah.
Okay, final question. The ultimate sci-fi dream. Terraforming. Could we ever actually change Venus? Make it Earth-like? Reverse that runaway greenhouse? Is that even remotely conceivable?
Terraforming Venus. We're deep into speculative, far-future territory here, facing planetary-scale engineering challenges that are honestly beyond our current or even foreseeable capabilities. But people have thought about it conceptually.
What kind of concepts?
The most common idea involves drastically cooling the planet, maybe deploying enormous solar shades between Venus and the sun to block sunlight. If you could cool it enough, the vast amounts of CO2 in the atmosphere might freeze out onto the surface as dry ice.
Freeze the atmosphere.
In theory. You'd have to get the temperature way down below CO2's freezing point. Then somehow you'd need to get rid of that frozen CO2, maybe bury it, maybe somehow ship it off-world, though the sheer quantity is staggering. Then you'd need to add water back, maybe by importing it from icy moons or diverting comets incredibly dangerous and difficult.
And deal with the lack of magnetic field.
Crucially, yes. Even if you fixed the atmosphere and added water, without magnetic protection, the solar wind would just strip it away again over time. So you'd need an artificial magnetosphere. Ideas here range from giant superconducting rings encircling the planet to a massive magnetic shield parked out in space between Venus and the Sun at the L1 point. There are even wilder ideas, like somehow spinning the planet up faster to try and restart the core dynamo.
So we're talking God-level engineering here.
Pretty much, these are fascinating thought experiments, pushing the boundaries of physics and engineering imagination, but they are firmly in the realm of science fiction for the foreseeable future.
Okay, so what does this all mean? We've taken quite a journey today, haven't we? From Venus as this object of ancient reverence, the bright morning and evening star, to understanding it as Earth's twin in size, but just a terrifyingly different world next door. That runaway greenhouse effect, driven by its thick CO2 atmosphere, really tells a powerful story.
It really does. We traced how our view shifted Galileo's phases, changing our view of the cosmos, Lomonosov spotting the atmosphere, the incredible persistence of the Venera landers, giving us our first look at that hellish surface, and Magellan's radar peeling back the clouds to reveal a volcanic world that might still be active today.
And then there's the ongoing mystery of the clouds themselves. Could they harbor microbial life? The phosphine debate really threw that back into the spotlight. And the, frankly, amazing, if challenging concepts for future human presence, not on the surface, but floating above it in cloud cities.
It's this combination, isn't it? A planet of such extremes, yet holding on to these tantalizing possibilities past oceans, current life, future habitats. It constantly challenges our assumptions about how planets work and where life might exist. Even its potential role as a testing ground for Mars missions adds another layer. Venus just keeps drawing us in.
It really does. It's a reminder of how diverse planets can be, even right next door. So whether it's that hunt for life in the clouds, the incredible engineering dream of floating habitats, or just its role in helping us get to Mars, Venus continues to challenge and inspire. What really stands out to you about our veiled sister planet? Is it its fiery past, its cloudy present with potential secrets, or the sheer human ingenuity it would take to truly visit? Something to think about. Until next time on The Deep Dive, keep looking up.